So Kata, please take it away.
Thank you for the introduction and for inviting me to participate in the World Logic Day. I labeled this as the AAL World Logic Day, but maybe the Southern Summer. It's definitely not summer in Edmonton. I even put it on this slide, on the first slide. I am sitting in Edmonton, and it's about minus 32 Celsius. With wind chill, it's something like minus 43 or so in the currently. My talk is based mainly on an already published paper, but I believe that it's not widely available paper. I wrote it for something, and then it was published in another collection. And so I would like to talk a little bit about so mainly, as I said, it's based on a paper, but I'm not going to read a paper. I would also like to, so there are several purposes behind this talk, beyond, of course, celebrating the World Logic Day. One of the purposes I would like to raise the, enthusiasm for sequent calculuses that I really like. And it's at least here in, for example, at our university, and I believe also at other universities, it's usually not the proof system that is taught in logic courses. So to accomplish this project, I would like to start with axiomatic proofs and argue that or show that they can be quite complicated. So let's take, for example, implicational intuitionistic logic. Here are two axioms: the principal type schema of K, as you can see on the right-hand side, the combinator K for the first axiom. For the second, this is the principal type schema of the combinator S. And of course, we have the rule, detachment, or modus ponens. And a big surprise, prefixing, so the formula that is usually called in the context of classical logic or two-valued logic prefixing, is a theorem of course, of intuitionistic logic. So how would we prove this? And so here is a proof that we might come up with. So first of all, let's take an instance of the first axiom schema, and it's obvious that this is the instance that we want to take. Then we take an instance of the second axiom. And again, this is what we want. Then we apply modus ponens to these two formulas, and we get a formula. Then we take another instance of the second axiom. It's a little bit lengthier. And we take modus ponens again with the fourth and the third formula. We take yet another instance of axiom A1 and one more modus ponens, and voila, we have the prefixing as a theorem. So I claim that this finite sequence of formulas all are instances of one of the two axioms, and otherwise obtained by modus ponens. So this is indeed a proof. And this is a relatively simple formula. It's a relatively simple proof. Nevertheless, I think that you might think that these 7 formulas, or the 6 formulas that finally lead to the 7th formula, are not exactly obvious how to find these formulas. And I have to say that I was cheating because, of course, I used combinators in finding these proof. And I claim that combinators do help or can help. Especially, I was, just for the sake of example, I was talking about purely implicational formulas. So here is a little bit of about combinators. I guess combinatory logic is also not widely taught. That's my observation here, even in computer science. So here is something about a little bit about combinators and what they do. So, for example, here is the reduction axiom on the left-hand side for the combinator S. I use lowercase variables x, y, z, and I use this little triangle kind of thing for indicating that this is the reduction axiom. In brackets, I show what the complete term would look like with all the parentheses, but there is a convention to omit the parentheses that can be restored by association to the left. And so that would be the axiom for S. Here is the axiom for K and B and C. These are fairly standard letters for these combinators. And S and K were the combinators that figured into the axiomatic system via their principal type schemas. So what is this typing is about? So the prefixing formula that I was saying that is provable is the principal type schema of the combinator B. And so here is an example how you can sort of briefly think about this, that this is a formula that has 3 antecedents in the implication. And if you think about those as X, Y, and Z, then the application in the prefixing formula of those 3 antecedents would lead us to D by modus ponens. And if we think about the function application as detachment in the case of the X applied to the result of the application of Y to Z, then we would also get D. I changed the letter so that the principal type schema of B and letter in the formula doesn't get confusing. So permutation is also a theorem. By permutation, I mean this formula that you can see where the 2 antecedents of an implication can be permuted. And well, if we use some combinatory reductions, then if we would have S of Sx applied to K of Y and applied to Z, then we would get X, Z, Y. And on the third line, in the sort of right-hand side of the slide, you can see that that is what C gives us if it's applied to X, Y, and Z. But of course, we would need to somehow get that K inside of the term that is on the left-hand side. And we could try to do that by the next reduction that I put up here, by S applied to BBS, applied to KK and XYZ. That reduces, in fact, to the SX K of Y, Z. So doing one further step, we also know, or if you looked carefully at the proof that I had on the previous page, then what I was really applying is I was applying the definition of the combinator B, which is S applied to K, S, K. So the left-hand side reduction here. And so if I substitute that definition into the previous term, then I get this lovely lengthy formula. It's not that long, so not totally long, but the proof in this axiomatic system is going to take, if I counted it correctly, then merely 23 lines. And on the right-hand side, that's intended to be a smiley face in a sort of a, without an icon. So I'm trying to say here that the axiomatic proofs are great, but finding these proofs, especially without even somehow utilizing the combinators, is very complicated probably. So finding all those instances of the axioms that are needed to produce even just the prefixing as a theorem is not really straightforward. So on the other hand, if we use sequent calculuses, then well, they are fun, and the task I argue becomes easier. So it's easier to find a proof. And eventually that is what the proof search is about. So for start, I will assume the original setting for sequent calculuses, which was introduced by Gerhard Gentzen in 1935. So a sequent, and I use for the separator here a turnstile. So between the gamma and psi, you see the turnstile, and so gamma turnstile psi is a sequent if gamma and psi are sequences of formulas. If we combine the formulas appropriately, and I'm trying to be a little bit vague here because the way how these formulas would be combined would be different in various calculuses. In classical and intuitionistic sequent calculuses, the left-hand side would be combined by conjunction, and the right-hand side, in the case of the classical system, would be combined by disjunction, but in some other cases, it might be more other connectives. And so I used here this pseudo notation with the ceiling and the floor to indicate that somehow the gamma and the psi are turned into a formula, and then the idea is that the result is such that the gamma implies the psi. I want to emphasize, because I feel that there is a lot of misunderstanding around concerning sequent calculuses. So proofs in a sequent calculus start with obvious sequence, which are called the axioms, so some axioms. And then the sequence are, as if, so informally speaking, are manipulated cumulatively. So these formulas in the sequence are manipulated cumulatively on the left and then the right-hand side of the turnstile. And so that's how we get finally to one sequent at the bottom, so to speak. So the proof goes from top to bottom. And here is a toy example. So let's assume that we have a miniature calculus in which we have one axiom, which is the identity, or A implies, or A turnstile A is the only axiom, but A is an arbitrary formula. And since I only have implication here, so that could be just an implication of formula or an atomic sentence. Then we have the implication, and it has a rule. What to do is to get an implication on the left-hand side of the turnstile. And we have a rule how to get an implication of formula on the right-hand side of the turnstile. So again, these rules are properly applied from top to bottom. And they, in this particular case, these operational rules or connective rules do introduce a connective into the formula that is as if created by these rules. Then the two following rules are labeled by C because they are related to the combinator C, although not directly. And so these are the so-called exchange or permutation rules. And so if I have these, then 7 lines give me, in fact, the proof of the permutation axiom or permutation theorem. At the bottom, I sort of squashed together 3 lines so that it fits on the slide. But you can see that it's pretty straightforward, the building up the formulas that are the antecedent and the consequent of the implication. So I claim that it is much more straightforward and more transparent or easy than the axiomatic proofs. So here is the propositional part of the sequent calculus that was introduced by Gentzen, although the notation is not following the original notation by Gentzen. And I tried to make the notation somewhat uniform on this slide. So I'm not following the original notation. However, I'm following the label. So it's the intuitionistic logic is denoted by LJ for J for the intuitionistic logic. And the psi here, but which occurs on some sequence on the right-hand side, is a slightly smaller psi than the psi previously, or the letters in this sequence, because of the fact that I want to use this as a special indicator of a sequence of formulas that is either empty or contains at most one formula. So on the right-hand side in the intuitionistic sequent calculus, there is at most one formula, not exactly one formula. That's why I didn't put a formula there, and it's restricted in cardinality. And by the way, could be a separate discussion whether it is a good idea. What essentially Gentzen was doing, that he defined the classical calculus and the sequent calculus as if one system, but the intuitionistic system has a restriction compared to the classical system. So just to put up some names and dates here, of course, the intuitionistic logic itself was defined or created by Arndt Heiting in 1930 as an axiomatic system. Gödel proved in 1933 that it's not a finitely valued logic. And so Gentzen in 1935 proved that the propositional intuitionistic logic is decidable. So at that point, this was a new result, and he used the sequent calculus for that proof. And I'm mentioning this decidability of the intuitionistic logic because the proof by Gentzen is very different from some of the proofs that have been used in the past 50, 70 years or so. So Gentzen's idea is the following. If we have a sequent gamma turns type psi, but again, this is a smaller psi as I used before, it is provable in intuitionistic logic, then it has a so-called reduced proof. And the reduced proof is a proof which comprises reduced sequence. And the reduced sequence has at most 3 occurrences of any formula on one side of the turnstile. So in the case of intuitionistic logic, of course, it reduces to the claim that on the left-hand side, but this could be also used for classical logic if you would want to have another proof of the decidability of two-valued propositional logic. And so Gentzen defines. Sorry. So Gentzen defines a top-down proof search. It is top-down in the following sense. So let's say that the question is gamma turns type psi is provable or not? So how we are going to proceed? Because of the fact that there is the admissibility of the cut rule, so we can concentrate on the subformulas of the given sequence that we are trying to determine whether it's provable or not. And we can generate all the reduced sequence that can be built up from the formulas from the subformulas that occur in the formulas that are in gamma, and if psi is not empty, then in the formula that is psi. So this is going to be some set, let's say, capital R. And then we are going to define another set of sequence, which are the provable sequence, and I denoted this by P here. And of course, we are interested only in sequence that are in this capital R set, because there cannot be anything else that leads to a proof. And then Gentzen wants to say that we are going to move sequence from the set R into the set P whenever it's possible. And to start with, we move all the instances of the axioms that can be formed from the subformulas of the target sequence. And then whenever we find that there is some sequence, let's say theta turns type B, that is provable from sequence that are already in P, then we move this sequence also into P. So it's sort of clearly sort of trying to build all the potential proofs that can be built without actually keeping track of the proofs themselves. So it's just moving sequence around in between two sets. So R is finite because we are talking about reduced sequence, and therefore P has a fixed point. So at some point, doing this repetition of trying to add to P is going to terminate, and then either the target sequence is in P or it is not. And if it is, then it's provable. If it's not, then it's not provable. So once again, I want to emphasize this is sort of a top-down proof search, because we start with the axiom and we look at what sequence from this set of sequence R is going to be provable. So next I want to, this is a little bit of, so it's a little bit out of time in a sense. You will see in chronological sense. Joachim Lembeck introduced the associative and non-associative calculuses in 1958 and 61. And his idea was to, in the case of the non-associative calculus, to change the comma to a binary connective that is not assumed to be associative or not assumed to be polyadic. So I call these in some places ropes instead of strings. So the parentheses matter. So that's the point of is the binary structural connective. And then the other difference, both from the classical and the intuitionistic sequence calculus defined by Gansen, is that on the right-hand side, there is exactly one formula. And on the left-hand side, there is a rope in the non-associative calculus. A notation that I will be using is the bracketing of a formula or of a rope inside of a rope that is denoted by gamma brackets in X. And this is one particular occurrence of X in gamma. I will also use the result of replacement in sort of within a rule or so by omitting the X slash notation, because slash is also used for something else in this calculus. So the non-associative calculus, Ln, is formulated by these 6 rules. Lembeck had linguistic motivations for defining his calculuses. And so he used a somewhat non-standard, at least at that point, I believe it was somewhat non-standard notation, this backslash and forward slash. You can think of those, of course, as implication and backward implication, and the dot is like a conjunction or fusion in relevance logic terminology. So we have an axiom and these 6 rules, and there are absolutely no structural rules. The associative calculus can be obtained if we omit all the parentheses that would distinguish between the displayed ropes here. So all those would be just A, B, and C, like flattening the ropes to strings. I put Lembeck's calculi into this talk for a couple of reasons. So one of the reasons is that I think sometimes people misunderstand that or claim even that really the COT is not admissible in some of these calculuses. That is not correct. Lembeck did prove the admissibility of the COT. It is not exactly like the proof by Gansen because of the fact that there are no structural rules. Perhaps somewhat unfortunately, he also used a term that was also used, at least in the translation of Gansen's paper, and maybe that leads to some confusion by some people. So the COT is admissible in both of these calculi, and I'm not going to go into any of the details of the proofs. And Lembeck also proved that these calculi are decidable, and in fact, the decidability. So these calculi are examples of sequent calculuses in which the decidability is a just corollary of the admissibility of the COT, essentially. So there is no other trick or nothing more is really used. So, for example, if we have here is a question: is this sequent, which contains some formulas here on the left and on the right, provable in either of these calculuses? Well, the idea, and this is an idea that is the more dominant idea in the past half century, is to assume that the sequent is provable and then try to see how first of all, as I said, that we can restrict our consideration for COT-free proofs. And then we try to see how this sequent could have resulted. And it could have resulted in finitely many ways, because there are 6 rules, and each of the rules increases the number of connectives that occur in the result of the application of the rule. And so we repeat this, and since there are no structural rules, as I said, each rule introduces a connective. So this decomposition going to terminate after finitely many steps. And we either have a proof or we don't have a proof. We just inspect what the result is. And this is an example of a bottom-up proof search. So we did assume to start with that the sequence was provable, and we were as if going upward in a potentially existing proof search proof. So that tree that was rooted in this presumably was rooted in this sequence. And this idea, the bottom-up proof search, was also informally entertained by Gensen, but it wasn't used in his decidability proof. But it was sort of formalized and developed by other people, in particular by Haskell Brooke Curry. He published a lecture notes in 1950, and this idea is very well worked out in that publication. So the idea, just to repeat here, let's start with the target sequence, and let's consider repeatedly what could result, what sequences could lead to this sequence. And then we repeat, and something happens. So, for example, going back to the intuitionistic calculus, we could ask whether A implies not A implies not A, which is sometimes called reductio, is provable or not. And on the right-hand side, I have an exclamation point. So in linear logic terminology, the answer is of course. So how would we look at this? So here is a proof, but how do we find this in using this proof search? Well, we could start from the bottom, as said, and I applied here to the, or I tried to find how this formula could have resulted. So what I have here on this slide is not the only way how this target sequence could have resulted, because, for example, it could have been the case that it was by right thinning or the right weakening rule, but we know that because of the cut elimination also holds for the intuitionistic sequence calculus, that the turnstile with empty left and empty right hand side is not provable. So that immediately means that we can sort of eliminate that branch from our proof search. We could go further up, and I added a couple of steps here. So at some point, maybe we think that there was a contraction applied to this top sequence, which is now a top sequence. But we could also go further, and maybe we applied further permutations and contractions. And in general, if we have a contraction applied, then we can further apply contraction, so to speak, a backward application, as it is sometimes called, but properly. So we could beef up the number of formulas. Of course, in the case of the intuitionistic sequence calculus, the sort of the shortcut is that if it's a reduced sequence, then, for example, I have here at the top, there are already 3 occurrences of A, so I cannot go further and add further copies of A by assuming that that was the result of a contraction rule, because that wouldn't be a reduced sequence, so that's out of consideration. But if we don't have the notion of reduced sequence, and it is the case that in various sequence calculuses it's not feasible to consider reduced sequence, then we can go off to infinity, so to speak. So contraction leads to infinity in the appropriate context. So it's that's the sort of the moral. And in general, it may be the case that the rules, so some of the rules may be, as I called it, contraction-like rules. So it's not necessarily the exactly the sort of the rule that was the contraction rule, let's say, in the classical sequent calculus LK. Nevertheless, it has some sort of flavor of contraction by reducing the number of formulas in a sequence. Then the proof search can be infinite, and that can be a problem. So somehow this needs to be controlled. And so Curry's idea, I put up here that Curry versus Kensen, because Curry's idea was in some sense diametrically opposite to the idea that was Kensen's idea. Kensen was trying to separate the rules that somehow affect the structure, the organization of the formulas in the sequence, and the rules that introduce connectives, quantifiers, etc. Curry's idea was that he wanted to eliminate the structural rules, meaning that, of course, to obtain the same logic, somehow one needs to compensate for the structural rules if they are not rules per se. And of course, this involves the modification of the possibly of the axiom and of the rules, the connective rules that form the sequent calculus. So first of all, Curry, in fact, in 1950 already introduced the idea of multisets of formulas, although he did not have the term. So he didn't use this exact word, the multiset, but he had this idea. And obviously, this is a simplification because if we permute two formulas, then we can permute those two formulas again, and we can permute those formulas. Of course, after a while, we get the same sequence, maybe in two steps, but nevertheless, the permutation rule can be applied again and again, and that can be a problem. So he introduced the notion of essentially of the multiset. So we don't distinguish between these two sequences, despite the fact that Gensen would distinguish between them. The weakening or thinning rules are eliminated via changing the axiom, and this does work for the classical and the intuitionistic sequent calculuses. For the classical, one could use the axiom that is on the left-hand side, where I have the gamma A turnstile theta A. For the intuitionistic calculus, of course, because of the restriction on the right-hand side, it would be only occurring on the left-hand side as a gamma. So we can sort of have several formulas in the axiom. That's the idea, and then we don't need the weakening. And the contraction rules, these are the most interesting for the purposes of decidability. Curry's idea was that the principal formula, that is the formula that is sort of introduced or new, so to speak, in the usual formulation of a connective rule in the lower sequent, is a formula that has to occur already in the premises. And here is an example for an intuitionistic rule. We could have this introduction of the implication on the left. And this looks like the previous rule, except that I have here now the A implies B in both premises on the left-hand side. And this is not a problem because the axiom allows us to have several formulas. So it's not a problem if we have more formulas on the in the premises. You might, by the way, think about what is the point of a rule, which, like the implication rule on the left, that introduces a formula, A implies B, which was already in the premises, but this can be thought also as an idea that is sort of leading to tableau systems and connection to certain kinds of tableau systems. Curry also introduced a further innovation, or it proved, in fact, a lemma. This is, especially in the relevance logic literature, it's often called the Curry's lemma. In some other literature, it's often called the height-preserving admissibility of contraction. And so here is the statement of the of a lemma, like Curry's lemma for, without specifying what proof system I'm talking about, but to give an idea, if there is a proof of a sequence, let's say gamma turnstile theta, and the height of the proof, which is just the height of the proof tree, is, let's say, n, then if gamma prime turnstile theta prime results from the previous sequence gamma turnstile theta by applications of whatever contraction rules we have either on the left or on the right or on both sides in the system, then gamma prime turnstile theta prime has a proof with height less than or equal than n. So it has a proof that doesn't require more sequence than the original sequence required. So let me add a further idea, and this idea is attributable to Saul Kripke. And he came to this idea in the context of solving the decidability problem for the implication of fragment of entailment, which at that point was simply denoted by I. So this was the I system. And this problem was brought to the attention of Kripke by Noel Belknap, and he solved this problem within like 3 months or so. So he very quickly solved this problem. I should maybe also mention that it appears that Kripke was primarily studying or reading another famous logician's book, I should say. Kleene in 1952 published his very widely used and well-known sort of textbook, which has some chapters or sections on sequent calculuses toward the end. And Kripke seems to have learned about the idea that I attributed here to, in fact, to Curry, to his publication from 1950, I believe through this textbook from Kleene. There are some differences between what Curry did and Kleene did. In fact, I think that Kleene is in some places a little bit sort of imprecise about the sequent calculus stuff. But anyway, so let me get to the implication of fragment of entailment. So again, this is an implication of logic. We have a couple of axioms, 4 axioms. And the first axiom is just self-implication. The second axiom is suffixing. So it's the principal type schema of B prime. The third is the same, or the self-distribution of implication. So it's the principal type schema of S. And then there is the restricted assertion. So it's assertion, but the formula that is the, let's say, the antecedent of this whole implication in A4 must be an implication. So this A implies B, and that is the restriction. And so this is a principal type schema of a combinator that can be described in sort of in the using well-known combinators. I take that C, B prime, and I are well-known combinators as this combinator C, B prime, I. And of course, modus ponens is a rule. So this is the whole implication of fragment of E, of the logic of entailment. Now R, the implication of fragment of the logic of relevant implication, which is often denoted by capital R, can be obtained by either replacing, or of course it could be just added as a further axiom. So either replacing A4 or just adding this new formula, which is assertion. And this is the principal type schema of CI or T. In Church's usage, it would be T. And I'm introducing the R because it has a little bit of a simpler proof. So the sequent calculus has a little bit of simplification because of the fact that this A4 is superseded by this other form of assertion. And so, or you can think about that the assertion as the specialized permutation. And so Kripke's idea, having studied this proof search technique, is that the contractions do not need to be required, like Curry's rules in fact require contraction because the principal formulas need to occur in the premises. Rather, let's just allow certain contractions in the rules. And in fact, it's possible to allow just minimal contractions. So for example, on the left-hand side, here is the form of a conjunction rule that could be introduced. Yeah, I could have had a C, let's say, on the right-hand side of the turnstile. It doesn't need to be B there, but the point is that on the left-hand side in the rule, the principal formula is repeated in the premise. On the right-hand side, the brackets in the lower sequence indicate that if gamma contained the formula A conjunction B, then it is possible to just take gamma as the lower sequence, or the left-hand side of the lower sequence, but it is also possible to retain the copy of A and B that is newly introduced, so it's a sort of more permissive form of the rule. And the reason for this is obviously because in relevance logic, sinning is not a rule in a sequent calculus. So as I said, R is a little bit simpler, so I'm going to talk about the implication of fragment of R. So we have an identity, and notice that the identity doesn't have anything on the left and on the right-hand side of the turnstile, except one formula. Then we have left contraction, and we have the implication that can be introduced on the left and on the right-hand side. So a modification of this sequent calculus eliminates, as you can see, the contraction rule disappeared. And instead, now we have on the left-hand side in the left introduction rule for implication, the brackets, which indicate that if there is a formula that occurs both in gamma and theta, then the number of copies can be reduced by 1 in the resulting lower sequence. And the implication of formula can occur in gamma, it can occur in theta, and it will be newly introduced. So the number of A implies B's can be reduced by 2 or 1 or 0. So once again, here the contractions are allowed, but not forced to happen. Then the decidability proceeds as follows. We have the Koenig's lemma, which is a general lemma pertaining to trees. Finitely branching infinite tree has an infinite branch, or it sort of can be viewed as a Brouwer's Fence theorem. We take a suitable instance of Curry's lemma, particularly proved, and it needs to be each time proved for each calculus for this particular sequent calculus. And you also use something that Kripke introduced, the Kripke's lemma, which is this can be stated as a sequence of distinct cognate sequence in which contractions of later elements do not yield earlier ones is finite. The term cognate sequence comes from Kleene, and two sequences are cognate if, since we are talking about a sequence where there is exactly one formula on the right-hand side, so it pertains to the left-hand side, it means that the left-hand sides of the two sequences that are cognate with respect to each other are such that if we would disregard the multiplicity of the formulas in the multisets, then the two left-hand side would be the same. So as sets, they would be the same sets of formulas. And so this novelty, the Kripke's lemma, is needed to guarantee finiteness. It does not have the property that it yields immediately a bound on the sequence, but it is guaranteed that it's finite. And it also has analogs in various other areas of mathematics like number theory. And so then 1 plus 2 plus 3 give us decidability, or gave Kripke the decidability result. So this combination, or this 1 plus 2 plus 3, where of course 1 is a general lemma, so that doesn't need to be proved again and again. Kripke's lemma is also general, so it doesn't need to be proved again and again. However, Curry's lemma is specific to each sequent calculus, and it has to be proved. And of course, I completely omitted here the cut, but cut would be admissible. So that is useful to show, for example, how to algebraize a sequent calculus, but I didn't even postulate it here. So those need to be proved for each sequent calculus. And this sort of sequence of lemmas obtaining decidability is what I call the Curry-Kripke method, because it, I think, primarily uses Curry's idea and then adds on to that components from Kripke's decidability proofs. And it has been extended in various ways, and I will mention 3 ways, and or maybe try to show 1 or 2 of these. So other connectives than implication could be added, and there is a rather straightforward way how to formulate the rules if there are other connectives than implication. So, for example, Robert Meyer, in his PhD dissertation in 1966, showed that what is called the lattice R, which is the non-distributive version of the logic of relevant implication, is decidable. Belknap and Wallace applied a somewhat similar technique to the implication negation fragment of entailment, although that is much less straightforward because of the peculiarities of E, so they have a rather complicated procedure. It's not as straightforward as for R. The second extension that I claim as a separate subtype of these extensions is to emulate proofs. And by this, what I mean is what Michael Dunn and I did for the decidability of the implication of fragment of ticket entailment. So we have a sequent calculus that we denoted by this LT, and then the intentional truth constant is in this superscript with this little circle around it. And this is equivalent to the implication of fragment of R extended with this intentional truth constant. But that's a pretty minor extension compared to Kripke's result. And this calculus, this LT circled T subscript arrow, contains exactly the sequent calculus that is for the implication of fragment of ticket entailment with intentional truth. And so we published 2 papers in 2012 and 2013 in which we show the decidability to, and maybe I will show a little bit more about how this emulation goes. But here the emulation, the idea is to start with the implication of fragment of R with intentional truth, and that is equivalent to this one calculus, and we can emulate proofs in this calculus that is LT circled T, and then just sort out which proofs are proofs in R and which proofs are proofs in the ticket entailment only. Sorry, which proofs are also in the ticket entailment. And then there is this idea to subsume special contractions, and this pertains to the decidability of linear logic. And Don and I have a paper about this, which we originally wrote in about 2015. And finally, it was published by now, since we are 2024, so it's 2 years ago or almost 2 years ago, and we claimed that linear logic is decidable. The idea is to subsume the special contractions that pertain to the formulas that have the exclamation point in front of them or the question mark on the right-hand side and can be contracted in linear logic under general contraction rules, and then deduce from that certain numbers and or calculate some numbers and prove the decidability. So I also applied this to the multiplicative exponential fragment of linear logic, and something called the normal linear logic that was defined by Kopylov, and it's not widely known that it's actually equivalent to linear logic. So here is a very quickly, let me try to give an idea how the decidability of T sub arrow goes. So again, we have a couple of axioms. In fact, I have here a 5 axiomatization. So this is a BB prime I W logic, but I have here the principal type schema of S and the principal type schema of S prime, which just permutes the two first antecedents of the principal type schema of S. And we have the modus ponens. So here is the usual contraction axiom, which is the principal type schema of W, and it could be taken as the force axiom instead of the A3 and the A3 prime. I mentioned this because the sequent calculus actually uses a rule that is related to the combinator W. What is notable that in the ticket entailment, the restricted assertion or the specialized assertion, and the restricted permutation or permutation are not theorems. So it is known, and so this causes a certain problem in terms of defining a sequent calculus for the system, for the logic. So here again, the semicolon is a binary structural connective, and here is the formulation that has two rules that introduce the implication on the left and on the right. It has an axiom, and it has 5 structural rules. 2 pertain to the intensional truth connective, the little t, and 3 of the bottom 3 rules are motivated or inspired by rules that were introduced by Dunn and Meyer in the structurally free logics, but there are no combinators introduced in these rules. It's only the label that indicates what the rules actually do. And then if we add these 2 further rules, then we get this LT with the circled little t, and this is equivalent to the implication of fragment of R. So the idea is that we do know from the decidability of the implication of fragment of R that there are finitely many so-called irredundant proofs. These are the proofs that adhere to the restriction that is stipulated in the Kripke's lemma. So if there is a formula that is provable, let's say A, then there are finitely many proofs, irredundant proofs. And these proofs can be emulated in the sequent calculus that is just above here on this slide. And there are finitely many ways to emulate those, or that's how we define it. There are finitely many ways to emulate each proof. So we have finitely many proofs eventually. And there is some issue about how we label some applications of the rules, but just to make sure, so we have a preference to avoid using the last 2 rules in this sequent calculus if unless they are absolutely needed. So for example, if there would be a application of the k sub t rule, but the theta structure would be t itself, then we can use the ki sub t rule instead. So we would have a preference for a rule that would keep the proof inside of the proofs that are the proofs in ticket entailment. So let me, I think I have here a couple of more slides. So here is the normal linear logic in sort of in linear logic or modal logic sort of notation. Perhaps what is notable is that there is no conjunction or negation in this in the language of this sequent calculus. Again, I'm assuming multisets for the sequence. In the original notation, this is how the sequent calculus looks like, with the upside ampersands and punctuation marks. And the decidability, the idea for the decidability, and this, it is similar to one of the proofs that we have for linear logic in the paper from 2015 that was published in 2022. So we can take this NLL system, and we can, instead of the restricted contraction rules, let me just go back for a sec. In the bottom line, on the bottom right-hand side, you can see the two restricted contraction rules. So they are applicable only on a particular side of the sequence, and the formulas that are contracted must have a certain shape. So if we extend to general contraction those rules, then the system is decidable, and the decidability proof is again follows or can follow this Curry-Kripke method, and it's pretty straightforward. Then what we do is we count the number of contractions on formulas that are of the form exclamation point A on the left or question mark A on the right-hand side of the turnstile. And we also calculate or also add in any contractions that occurred on subformulas of these formulas in each of the redundant proofs, and we attach the maximal number as the heap number to those formulas. So once we have this heap number, this is going to serve as a bound for our proof search. We do a proof search we go back into NLL, so this normal linear logic, and we restrict the number of applications of the restricted contraction rules by the number that is the heap number for the particular formula that is of the form that could be contracted by those rules. And this restriction, the fact that there is a finite number attached to that formula, means that there are finitely many applications of contraction rules that are applicable, so that avoids infinity. So here is a conclusion. In fact, I just have one conclusion here, I believe, on the slide. Sequent calculuses are fun and fruitful, at least in the proofs of decidability results. So thank you for listening to this, and here are some references.